Excellent. Okay. So Dr. Liang currently has two students, one working in that simulation area, one looking at the laser plasma experiments. Okay. My work is similarly varied. I look at the more elemental aspects of particle acceleration in astrophysical shocks. We see the non-thermal particles, and we know we have supersonic flows ubiquitous in the universe in lots of environments. In supernova remnants in our galaxy, in pulsar winds in our galaxy, in gamma ray bursts out in the distant universe. And also in blazars. These are the jets that are associated with supermassive black holes at the center of galaxies distributed in the universe. So I look and try and probe what sort of particle distributions we expect in turbulent shock environments. So these are just tidal waves in the universe, and they dissipate through plasma physics mechanisms and accelerate particles. So we look at the properties of those. I use now, because of my connections with Fermi, I'm doing a lot of work on specific sources, on interpreting the data that is coming hot and fast. This is NASA's hottest science experiment at the moment. And we've got just dozens and dozens of results. It's basically every day we're sort of like dealing with what's hot off the press and trying to work papers out, to get papers out with the new results. So it's a very exciting field. And it's only been up for 18 months. So the other area is in neutron star magnetospheric physics, where we focus on trying to produce radiation that we see in sources, principally pulsars, and a very highly magnetic variety of that called magnetars. And I have two students working in this area, Zora Wawadia Singh and Sarah Story. And the goal is to try and explain the radiation mechanisms and find out where in the magnetosphere of a neutron star, is it down near the surface or is it a long way out, the emission occurs. We have very good ideas. The physics that we report in is very different from this. This is mostly plasma physics and electrodynamics. In the neutron star, we're dealing with strong field quantum electrodynamics, which is just a very different and exotic and fun field that I've had since my late undergraduate days. So the particle acceleration, basically particles in the shock, they just diffuse around, they bash around in magnetic turbulence. The field is all tangled up, and basically magnetic mirroring on small scales transports the particles around and diffuses them, and each time they diffuse between regions of converging velocity flows, you get acceleration, energization. That's just basically, if you imagine you had your walls converging and bounced a tennis ball elastically off the wall, you find in our frame of reference it accelerates. So this is what's going on in plasmas, and we see plenty of evidence that this is going on. We actually measure it in the heliosphere. We actually see the particles being accelerated. So we think the idea was originally due to Fermi in 1949. What we'd like to do is produce, this is just a sample of what we would get from this type of system that is beyond the thermal. This is the Maxwell-Boltzmann distribution, and then you have a look and see what the non-thermal distribution looks like. And there are a lot of model parameters that you can deal with, but they all give us insights into the environment of the shock, which basically means what is the large-scale structure of the magnetic field of the shock. That's really what it is, and that's what we like to do. Next slide, please. On the neutron star side, we can come up with models where we predict this is basically a spectrum. It's a very broad spectrum. The spectrum is produced by, in this particular case, by Compton scattering. But it's not Compton scattering that you know. It's Compton scattering in strong magnetic fields, which is necessarily resonant with the cyclotron frequency. So basically, there's a certain probability, the Thomson cross-section, and then you get into the resonance, and away it goes. It's basically about 2.5 to 3 orders of magnitude stronger. So it rattles around in the resonance, and you produce this continuum spectrum that eventually turns over at the maximum permitted by Klanishina kinematics in the Klanishina regime, and it's very hard to see, but you get very strong polarized signals. Okay, so the polarization state of the photon gives you a different prediction for the spectrum, and this is a goal for future space telescopes where we would like to measure polarization. These are very high energies. These are above 1 MeV is what we're looking at, around here, and we want to be able to measure polarization, and that's part of the initiatives that I'm involved in, is trying to get measurements of polarization in high energy astrophysics. We already have one now approved with NASA that I'm working with, called the Gravity and Extreme Magnetism SMEX, Small Explorer, GEMS, and it's in the X-ray band. It's going to look at neutron stars, active galaxies, and galactic black holes, and measure polarization at about the 1 to 5% level. And this is going to be a very exciting field because we've never done this before. So Next slide. Okay, Dr. Vasari, his focus is mostly on active galaxies, and specifically the so-called class called blazars. Blazars, so active galaxies are a supermassive black hole, typically between 10 to the 7 and 10 to the 9 solar masses. In the center of galaxies, they're out there everywhere. And they suck in material, and that's accreting, and they produce an accretion disk, and then they blow off in a relativistic jet, more or less like a gamma ray burst, but much larger in scale. A relativistic material that we measure is typically moving at Lorentz factors between about 3 and 100. So it's very fast, not as fast as a gamma ray burst, but a lot of energy. And we see these jets. We see them in radio, we see them in optical, we see them in X-rays, and we can't resolve them in gamma rays because the gamma ray telescopes don't pixelate the sky as well as X-rays and radio telescopes and optical telescopes. But we can get a lot of information. We get spectroscopy, and that's what's coming out of, for example, Fermi. Dr. Vasari looks at the multi-wavelength approach and looks at the broadband spectrum, which is a very common approach in astrophysics these days, and it's pinned by high energy astrophysics. What we tend to find is that most of the energy is produced in the X-ray to gamma ray band. So that's why we do this. We explore this. We know that the energy dissipation is mostly going on there, but there's simultaneous information from optical up to radio, optical, X-ray, and gamma rays. We can put this all together, and he sort of looks at population studies, phenomenological modeling, and the multi-wavelength approach to try and disentangle what's going on in your active galactic jet. This is the jet beamed out relativistically, and here's the accretion disk. Okay, next slide, please. So he will look at time variability. There's a lot of, he goes and he digs, there's a lot of data out there, and so I'm about to wrap up. And so it's a bit hard to sort of discern that, but what the idea, the goal is to go and determine the structure of this jet. This is like a cut of that jet. Do you have magnetic fields that revolve, that rotate around like this, or spiral in sort of a helix, or are they sort of beamed in sheets? And that's, so we'd like to explore that. So he has 2 students currently working in this area of trying to disentangle the structure of jets based on time variability studies and ensembles of information, phenomenology. So,
thank you, Professor Perry.